All right, welcome to this video on section 12.1. We're going to introduce rational functions in this section, and for those using the ebook, this is in the introductory algebra text, that's section 9.1 there. Okay, so the definition of a rational function is here on the worksheet. Says that a rational function is a function of the form r of x is equal to p of x divided by q of x, where p of x and q of x are polynomials. So that is, a rational function is a ratio of polynomials. Okay, so here are some examples of what these things could look like. So for example, I'm going to have, say, a polynomial like 3x squared plus 7 for my numerator. Okay, my denominator, I want another polynomial, maybe something like 2x minus 5. Okay, this is a ratio of polynomials, and so we call that thing a rational function. Okay, and by the way, this word rational really is a reference to the ratio, right? This is just a special kind of ratio. Okay, cool. So let's now check out question 1, where it says to consider this rational function. So r of x is 1 divided by x minus 3, and our job in part A is to complete the table of values to the right. All right, so I've just included the table over here, and in order to complete it, okay, we're just going to plug these values of x into our expression for the function and see what we get for the corresponding output values. So let's see, if x were 0, I'd get 1 over 0 minus 3, and this is 1 over negative 3, which is really just the same thing as the opposite of 1/3, right? So negative 1/3 there would be my output. Now if I plug in 1, I'll get 1 minus 3, that's negative 2, and 1 over negative 2 is minus a half. If I plug in 2, I'll get 2 minus 3, that's negative 1, and 1 over negative 1 is just negative 1. And now if I plug in x equals 3, something interesting happens here. I get 1 over 3 minus 3, which is 1 over 0. Oh, and 1 over 0, this thing is not defined. I cannot divide by 0. And so for that reason, the table, I'll go ahead and just say NA. Not applicable, right? There's just not a well-defined output if x is equal to 3. All right, cool. So then pressing on, if x were 4, 4 minus 3 is 1. 1 over 1 is 1. If x were 5, I'd get 5 minus 3 is 2 in the denominator. So I'd get a 1/2. For 50 for x, that'd be 1 over 47, right? And then finally 1 over 97. Okay, so these are the table values, and now on to B, where it says r of x is undefined when. Well, going back here, it's going to happen when there's a division by 0, and we see that that occurs when x is equal to 3. All right, so that would be part B. For C, r of x, is that ever 0, right? Is there a value of x such that r of x is 0? Well, what would that look like as an equation, right? This would be 1 over x minus 3. That's our r of x expression. We're asking, is this thing ever equal to 0? And the answer here is no. And why is that? Well, one way to explain it is that, look, the thing I have on the the left-hand side is a fraction. And the only way that a fraction can equal 0 is if its numerator were 0. But see, no matter what I plug in for x, this numerator is just a 1. And this is, well, not 0. And so any value for x I substitute in here, right, I'm going to get 1 divided by something. And that's just never going to come out to be 0. So that would be a way to explain it. Another way to explain it, so I'll put a little note here, is just to really go about trying to solve this thing using algebra and seeing what happens. Okay, so we're asking, is this equation true for any values of x. Well, here what I'm going to do is I'm going to multiply both sides of this equation by that denominator. So I'm going to clear out the denominator, so to speak. So I'm going to divide out the x minus 3, because this divided by itself is just a 1. And so that's going to leave us with a 1 on the left. But on the right, I get 0 times, well, anything is going to be 0, right? 0 times x minus 3 is 0. And this, of course, is false. And so for that reason, we're saying, look, right, solving this leads us to this contradiction. So in other words, there is no value of x that would make this equation true. So again, our answer would be no. All right, cool. And now on to part D, where it says to sketch the graph of R, and then does the graph ever cross the x-axis? Well, I'll go ahead and pull up graphing template here, and I've just filled in the values that we had from our table from before. So what I want to do is go ahead and just plot these ordered pairs. So 0, negative 1/3, say is like down here. Notice I'm being a little bit lax about the vertical scale. This is just a sketch, so we don't have to be super precise, just to get a rough feel for what the graph looks like. So 1 comma negative 1/2, well, here's 1 for x over here. We're going to be a little bit further down for y. 2, negative 1, that's going to be, say, down here. And then at 3, right, our function was not defined, so for that reason, I'm going to go ahead and just put a dashed vertical line through 3 for the moment to indicate that. 4, right, the output there was 1, so we'd be now at a positive 1, so up here. And when we plugged in 5, we got a half, so say down here. And then for 50 and 100, right, these are clearly way off the chart, but I can see, right, for these larger x values, the y values, right, are progressively getting smaller. I go from a half down to a 47th, down to a 97th, so on and so forth, okay? So putting that together, I'm going to get, say, these 3 dots connected by some curve. And then up here I have these 2 dots doing something like this. And since, again, right, y is getting progressively smaller as x gets bigger, that's going to tell me, right, my graph is, I'm going to move way out to the right because x is getting bigger, and y is going to become really, really small. So I'm going to maybe, approach the x-axis kind of like that. All right, now what's going on right around 3? Like, what if we plugged in something like, say, 2.99 into our function? So just to the left of 3. Well, if I did that, I'd get 1 over 2.99 minus 3, which is 1 over a negative 0.01. Oh, that's negative 100, right? So it's really big and negative, okay? And so what that's telling us about the graph is that, oh, we're going to be essentially following this vertical line way, way down here, right? I mean, 2.99 is just shy of 3, and we're going to be way, way down there, it appears. Okay. What if I plug in something just to the right, like let's say 3.01? Well, here I'm going to get 1 over 3.01 minus 3. That's going to be 1 over positive 0.01. That is equal to 100. So that's telling me what? Well, if I'm just to the right of this blue line, right, my graph here is going to be way up here. Right, my outputs now, my y values, are very, very large if my x value is just slightly to the right of 3. Okay. Okay, cool. So let's go ahead now to fill out just a bit more detail. I mean, this is a perfectly fine sketch, but here is our function here. Just I've gone to desmos.com and put in our function equation, as well as that break in our graph at 3. And again, you can see here that when we're really close to 3, say from the right, my graph is going way, way, way up here, this vertical line. And then if I'm just to the left, right, I'm going way, way, way down there. Okay. Now we're going to call this dashed line here, this has a special name. It's what's known as a vertical asymptote. Okay, asymptote, here we go. Cool. And the other thing I want to highlight here, right, is that if I were to say zoom way out and go over to, like, say when x is 50, right, we saw that the output there was 1/47th, which is small, but it's not, you know, it's not 0, right? It's about 0.0213 in decimal form, roughly, right? Okay, so what happens if I go, say, way, way, way out to the right? Like, let's say I go, I don't know, let's go to like 500, right? Where is my y value now? Well, I'm zooming, zooming, zooming. Am I at 0? Am I going to hit the x-axis? Well, no, right? If I zoom in far enough, right, when x is, say, 500, my y value is really small. It's 0.0021, sorry, but I say 0.02012. Yeah, yeah, it's small, but it's not 0, right? And the point I'm making here is that, you know, when the question says, does the graph ever cross the x-axis? We can see our y values are getting small, but did they ever actually hit 0? And the answer there would be no. Okay, so let's make a comment about that down here. So does the graph cross the x-axis? And yeah, our answer here is a no. Okay, and a reason for that, beyond just playing around with the graph on the calculator, is to say, well, look, if we were at the x-axis, then y, which is equal to r of x, would have to equal 0. And we saw in part C, right, that that really never happens, because that's equivalent to saying that 1 over x minus 3 here would have to equal 0. And this just simply never happens. Okay, so we can say here this never happens. And so the answer to the last part of question D is simply no. We do not ever cross the x-axis. Okay, so now for this reason, okay, we're getting close, really as close to the x-axis as we want if we go really, really far out. Right, so if I continue to follow our graph way out here, I'm going to get infinitely close to the x-axis, but I'm never actually going to hit it. Okay, so for that reason, I could say that this horizontal line now, this is what's referred to as a horizontal asymptote. Okay. Well, this is going to be a good place to stop for this problem. I will see you in question 2 in the next video.